Okay, that is Bentley PondPack as PondPack. Create new. Say no. I'm just following the tutorial which I found from internet, online tutorials, Texas University actually. Save as just simply to see the potential. Tutorial, yeah. So this is just simply tutorial, yeah. And then project. See, this is titled to tutorial. Yeah, it's just tutorial, yeah. Engineer is told the man. Hydro engineers. Yeah, so this is simply an exercise. That's all. Just to show the potential of PondPack, Bentley PondPack, what it can do for us. See, yeah, it's a wonderful software. We can design a pond. We can make a scenario. We can design. You see, we can make scenario after pond construction and before construction and so on. There are other uses as well. So now we have done everything. We can create our. Okay, the unit must be checked. You see here. Unit here, international US. Just click here. Drawing here. This is not schematic. Just a schematic. You see, we are going to draw our catchment and pond and so on, and that is simply a schematic representation of our catchment, our pond, our well, our orifice, or something like that. You see. So here it is how we construct. Just click here, control, just click. So right click, done. This one, and the next is pond, control, click, right click, done. The next is we need some pond outlet. Just here, click and just put it without leaving the left button. Click your mouse and right click here, outflow. Yes, click. You see, now done. Now we have outlet. This is pond and catchment. So we have to connect these two. Now click here to deactivate. Okay. Now to just put some properties here to change some to the property of the catchment, we have to click here, double click. You see, local rainfall, yes, true. Storm event, edit. Here new, we can click time lapse. Here also dimensionless. Click here, just click here, select. Now we just 71. This is just given in the tutorial. So see, doctor. I think, I mean, the idea behind this thing is that we are going to generate a storm event, you see, from something, from a data that is already or synthetically prepared or something like that, like a synthetic hydrograph, you see. There is like a unit hydrograph, you see. So just synthetic hydrograph is developed just simply from the catchment characteristics, slope, length, area, catchment shape, something like that. They can you see construct a hydrograph out of those stuffs. And like a unit hydrograph can be extracted from a hydrograph of a storm event, you see. For example, a 3-hour storm event, a 12-hour, 6-hour, 24-hour storm event. We just develop a unit hydrograph. In that unit, from that unit hydrograph, we can generate a storm event. Similarly, you see, a unit hydrograph is that amount of discharge or Q that makes, or the runoff that makes 1 centimeter depth in the whole, you see, area of that catchment. That is the unit hydrograph. You see, during the specified, for example, if the storm event is a 3-hour storm event, during that period, the amount that makes 1 centimeter depth of runoff, that makes the unit hydrograph. So after we just make a unit hydrograph from the relevant, we can develop for different durations, storm durations. So that is it. So we are now ordering at a return event 10 years. We want it to develop for us a 4.5 depth, you see, inch, and a 2-hour duration. So we are going to generate. So it generates for us a hydrograph depths. I mean time depths. Information, you see, this is the depth, this is the runoff depth, I think, the hour is this. So that is it, I think, if I am correct. I'm just using my hydrology skill and gas, you see, intelligent gas. Okay, that's all. Yeah, that's so we have close. We have already some event. We have to put it here. Unit hydrograph. Okay, this area user defined. Given this curve number is given, area is 10 acre. You say okay. Time of concentration also given, it is 30 minutes, so 0.5 hours. Okay, that's what we have here, I think. So now we can click here and click on the pond. This is the pond outflow node must be, you see, we can select from. Okay, we connect them. Okay, so now this one here is a pond type volume A, because we have a data elevation area that we just simply, the pond type is elevation area, then we have a data, so just click, here is the data, you see, copy, Control V, you see. Now we have elevation, pond area, that is, it seems, a proportional type. So that's it. We can see here, you see, like this. No, here, pond volume result table, I think, you see. Yeah, that is it. So it is already here. mm, that's all the pond entrance here. Click the entrance and oh yes, the upstream pond is the PO1. Okay, that's it. Now outlet structure. Yes, we call here and a composite structure. Okay, here you see new composite. Then you see we just click here and select from the picture the pond, so automatically it enters the elevation, minimum and maximum elevation of the pond in tailwater free outfall. So that's all. So because we have two outlet structure, a weir structure and an orifice, so we have to put them here, I think. So orifice, you see the weir structure has an elevation. The elevation is also given the 105 something. Yes, 105. And the flow is a forward flow type. And the weir type is rectangular weir type. The coefficient is given 2.6, just simply. And the weir, you see, is suppressed or contracted, I think. Contracted given, but it can be suppressed or contracted. The weir length is given 15. So this is the information required to run the model, you see. The orifice also given. They said that it is 6 inch and this is forward only flow and this is 100. That is the level of the we can run now. We can run and see. You see, this is the composite. Both structures do have pond-water surface elevation and flow. This is for both relation. You see the flow, when the flow, the sum of the two, and the pond stream. You see, that is it. And when it is the orifice, you see, when it is the weir, you see, you see the advantage of this software is you see you can automatically change suppressed and see the results. You see, you can run and see when it is suppressed, it is 110 for the maximum water surface elevation, and you can change and see contracted weir structure, rectangular contracted weir. So like this, that is it. So you can see that you see, just simply to show what a contracted, this is suppressed weir, you see. This is a suppressed weir, like let me show you. This a contracted weir is like this. Just simply like this. Like this. Now a little bit like this. If we can make, okay. If this here, we assume that it is, you see. This is the well. So this is the level, and the water flows in this direction. It falls here, you see. Maybe we have a still basin here. Still basin. This is upstream side. This is upstream side. This is a contracted weir because the water, you see, comes like this and it will be contracted, and see there is a loss because of constriction, you see. So the discharge decreases and also the coefficient also increases, I think. Okay, that's it. The suppressed one is just simply like this, you see. For example, if this is like this, this is just simply a straight line. I can, let me make myself comfortable and you see. Well, why don't I, let me, this is, if this is upstream, you see, and the water comes in falls like this. There is no construction or something like that. This is a freeboard of the river or maybe the land. Here maybe you have a stream basin. You see, there might be a stream basin. There might be buffers or something like that, or some like a structure to just simply store some water, so the water flow comfortably here. So see, then it dissipates its energy and flow downstairs, so it will not erode or something like that. That's a suppressed type of wear, you see. Anyway, that is it. That is it. So that is the theoretical part of the wear design or something like that. This we have done everything here. Here is good. We are good to go. So here we have to put this thing. Okay. See outlet structure. Here I think rainfall. I think rainfall here. Okay, the local rainfall is this. We did it. Okay. So what remains is we have already done this. That's all. I think we can run the model, I think, now, because everything is in good condition. All the data okay, let us validate. I think error. There is something we forgot. Okay, here global. See, we have to put, sorry, we have to, I forgot to put this on. This is a global storm. See, here it is. This means global storm event means just using for everything from here. It doesn't mean that it's workload or something like that. This is just for it's global general for every, it's a data for to be used for every calculation in the system. It means. So that's it. We can validate now. You see, no validation issue found, so we are good to run the model now. Okay, compute. You see, that's it. So this is the result. We can see, I think, graph or something like that. Yes. So you see, okay, so you see what we have got is, this is elevation time curve. See, at the first hours, see the water comes fast because the inflow hydrograph, there's a lot of water coming from, and the outflow is less, small. So that is the use of the pond, just to attenuate, retard, you see, weaken the flow, so that the downstream side or the people or village there might be, see, will be saved from the inundation or the flood or something like that. Anyway, you see, we can see in the hydrograph that a lot of water is stored in the pond, and some water, small water, flows out. So that's it. That's the design. You see, we can also change this one and make this one a result. You see, only to see some like this. Just okay. See, this is a volume, this is elevation time curve, this is volume time curve. You see, through time the volume increases and the elevation also increases. Yeah, at a certain period, you see, when the elevation, at a certain period, when the peak discharge, when the peak decreases, the volume also starts decreasing, you see, because the outflow continues slowly. You see, that's so. That is PondPack, you see. We can also use PondPack for scenario analysis, you see. There is a Kickstart lesson also here, a tutorial, you see, pond design from start to finish. You see, you can have setting up, how you set up the project and rainfall, everything, you see. So it's a wonderful software to design a pond. See, we don't need just simply running and having some knowledge, hydrology or engineering knowledge. See, we'll design something like that. So that's all. If you have how we can design a well, for example, we can design this well can be designed. You see, we can say here. Where just simply can be calculated discharge. You see, the C times L times H to the power of 3 something. This is the formula to design in cubic feet second, I think. This is for where like a broad spectrum weir or something, a weir type like suppressed or contracted, or like this one. It may be like this one, or just simply just a broad spectrum. For a V notch, we have another, I think this is the tan something, tan theta over 2 H something. It's different for a weir type like this, you see. Yes, that's different. Orifice, for orifice, there is also, for orifice, Q is given like coefficient times area times 2G you see, that's it. Sometimes they put it like 64.4 times h. This is because g is equal to given 32.2. So that is our first formula. If we have ideas like this, then I think we know what the pond is doing, and we can design it. Even our pond, we just simply design our pond. If we are a farmer, farmer can design his pond just simply using Bentley and following the steps. So that is it. That is about Bentley. It's a wonderful model. Lot of information. You can investigate more, you see, by yourself. Once you are able to run the model, then you slowly can do a lot of things, you see, because there is also a tutorial here, some theory information, so you can make use of all those information, and if you are interested, you can do it. So that's it.